All right. So today, or this lesson, I really just want to talk about, and I really want to consolidate some of the laws of reflection that you would have experienced in the last, doing the lab that you just had completed. The first law of reflection that I really want to talk about is the angle of incidence is equal to the angle of reflection. Okay. In the video, you would have seen, the ray box hitting a flat mirror, and we know that this is a flat mirror because of the hatch marks here. Okay. You have your normal, which is perpendicular to your plane mirror. So it's drawn at a 90 degrees, and your normal is drawn at the point of incidence. The point of incidence is the point where the light ray, boom, hits that flat surface or hits that plane mirror, okay, and that is the point of incidence. And the normal is drawn at the point of incidence, okay. You see that your angle of incidence, which is your angle of is the angle between the incident ray and the normal is equal to your angle of reflection. And hopefully you would have seen that in the video and you would have gotten that idea with the ray box hitting and then the angles equaling the exact same. The angles equal the exact same. Okay, so hopefully that was pretty obvious for you when you did the lab or when you watched that video. Okay. Maybe something not so obvious is the second one, but the second law of reflection is that incident ray and the reflected ray and the normal all lie within the same plane. Okay, we talked a little bit about planes in the introduction yesterday, and really it's just that your incident ray, your normal, and your reflected ray are all within the same plane. I have my incident ray coming in here, okay, and it's bouncing off, but at the same time it's staying within that plane. It's not shooting off this way or shooting off down here. Okay, it's pretty predictable, and it's within that same plane. All three of those are within that same plane. Okay. Now, when we see things, what we're actually seeing is not just one ray. I know in that image, in that video, we just saw the one ray of light coming out, that incident ray of light coming out and hitting that flat mirror. Okay, but in real life, what happens is you actually have multiple incident rays, and they're all traveling parallel to each other. And we know that because we know that light travels in a straight line, right? So all the rays are traveling in a straight line. You could tell that in this picture easily because they're all traveling parallel to each other here. Okay, they all travel, they hit this flat surface or this plane mirror right here. And again, we can tell that that's a plane mirror because the hatch marks here, so you have your reflective surface on top here. Okay, and they hit that plane mirror and they bounce off and go to our eyes. Each incident ray has a point of incident. At the point of incidence, you have your normal. Your normal is drawn perpendicular to the flat surface, right? At a 90 degrees. So you have your normal here, you have another normal here, you have another normal here, and you have another normal here. On a flat surface, okay, like I said, all of these rays will form, the incident rays will all form the exact same angles of incidence and all have the exact same angle of reflection. Okay, it's pretty easy to understand that and pretty easy to see that based on what we saw in the lab. So in the lab you saw one light, but pretend there's thousands or even just four rays. They're all parallel. The incident rays are all parallel, therefore, and they all hit a flat surface. Therefore, our reflected rays are all going to be parallel. And this is known as specular reflection. And specular reflection you can see specular reflection, say, when it's really dark outside and you're looking out the window and you have the lights in your bedroom on and you look out the window and you see a reflection of yourself. Okay, and that's specular reflection off a flat surface. Another example of specular reflection would be when there's a really calm day outside, when there's no wind. It's just really nice. There's no wind, there's nothing. The lake or the pond is really still, and you see a beautiful reflection of the scenery. In this case, a mountain with trees. Okay. Again, it's just because you have a very flat surface. The rays that are being reflected off the mountain are hitting this flat pond or flat lake and reflecting, and then we are seeing this reflection that's identical to the actual image here because of the plane surface. Okay, another thing that I wanted to cover was this idea of what happens when we have a rough surface. Okay, the laws of reflection still apply, but the incident rays hit the surface at different angles due to the irregularity or the irregularity of the actual surface. So if we take a look here, okay, we see our incident rays are all still traveling in a parallel line, but they hit the surface or the mirror or whatever it is that they're hitting, okay, at different angles. Okay, you still have your point of incidence, but again, your normal has to be drawn at the 90 degrees to the surface at which the point of incident is happening. Okay, so you see your normal is drawn this way, the normal on this incident ray is drawn up here, the normal of this incident ray is drawn back this way, okay, and the normal of this incident ray is drawn right here. Okay, and the laws of reflection still apply. However, the image that you see that is being reflected is not as clear or not as bright as, say, when you have a very flat mirror. Okay, and the result is the reflected rays that bounce off are all scattered all over the place in many, many different directions. And that would have been, that's probably pretty clear. So if you had a piece of aluminum foil, it's really hard to, you hold aluminum foil up, okay, and you crumple it a little bit and then you open it again. You try to look in the aluminum foil, it might look like you're a little distorted or it's hard to tell what the image is. Um, and that's because you have light rays bouncing all over the place. You don't just have one flat, smooth um, image. Okay, and that's again because of the irregularity of the surface of the mirror that you're looking at. Okay, an example, and this is called diffuse reflection. So diffuse reflection is with a rough surface. Again, your incident rays all hit at the same, they all travel parallel to each other, but they hit at different angles, causing the reflected rays to bounce off in an irregular fashion. The laws of reflection still apply, so my angle of incidence is still equal to my angle of reflection, but my normals are all different. Okay, and my normals are all different because my normals are drawn at a 90 degree to the surface at which my point of incidence is. Okay, an example of diffuse reflection is again with the aluminum foil. You're trying to look at the aluminum foil that's been crumpled up. You can't really tell the image. That would be diffuse reflection. Or also when it's a little bit windy and there's a little bit of, I wouldn't say waves, but roughness to the water, okay, or it kind of causes this distortion. You can't really tell what it is, that reflection on a lake, as opposed to specular reflection. All right, so hopefully that solidifies some of the concepts that were demonstrated in the lab um, for you. If you take a look at page 486, I'd like you to complete numbers 1 to 6. You can also read pages 484, 485, and this will help you with these questions as well. Okay, if you have any questions, just let me know. We'll talk to you guys soon.